So you know two consecutive numbers is an even and odd, which will always produce odd. Another way to say that is from this notation too, because if x and y are consecutive, x plus 1 and y plus 1 are also consecutive. So it'll be an even times an odd, which is even, and then minus 1, which makes it odd. Okay, so we know it's always going to be odd. What are the possible outcomes? This is actually a pretty interesting way to say it, because assuming that I'm only allowed to put in positive integers, are we going to assume that? No zeros around, only positive integers. So if my output is some number, then what that means is, well, let's see, if x and y are positive integers, then x plus 1 and y plus 1 have to be at least 2. And when I multiply them, I get n plus 1. So if n plus 1 can be factored into two integers that are both at least 2, in other words, if n plus 1 is composite, then I can make it. And if n plus 1 is prime, then one of these things has to be 1, and the only way to make it is if I put a 0 in. So the key question is whether n plus 1 is prime or composite. That tells me whether I can make n, which is pretty neat. So that kind of answers this question. The smallest number you can't make, well, you can't make 1. That's probably the smallest. I don't know, maybe assuming you start with all the cards 1 through 100 already. So what's the first thing after 100 where n plus 1 is prime? 103 sounds pretty prime to me. Feels prime anyway. So that would mean 102 can't be made. 102 doesn't sound so bad, right? It seems like, oh, there's got to be some way to multiply and add and get 102. When you look at this, 102 looks very doable. But when you look at this, you realize that really to make 102, you have to multiply stuff that equals 103. And 103 is prime. So again, the power of having the multiple representations is pretty nice. Okay. If you know the output, can you find x and y? Well, if n is a product of just, if n plus 1, I mean, is a product of just two different primes, or 1 prime squared, then there's only one way to factor it like this. But if n plus 1 is more complicated than the product of 2 primes, then there'll be many ways to make it. Pretty cool. Okay. All right, answered that. Kind of answered that too. Kind of answer that too. It depends on how many factors n plus 1 has, right? So that's kind of exciting. Kind of answered that too. Didn't answer that, but I'm not going to try to right now. All right, and sort of answered that one. Okay, so we're left with what's the output? Cool, we kind of answered pretty much all these questions. This is nice. All right, so one way to think about it is, again, in terms of an invariant. We can think about if we have a bunch of numbers, whenever we want to combine them, what we're going to do is we're going to add 1 to each of them so that we can use this rule. So we're going to have original land and plus 1 land. And up here, the operation is x times y plus x plus y, which is kind of a mess. But down here, the operation is multiply and subtract 1. Right? Well, really, if I go back up to original land, that's the subtracting 1. This is the plus 1 to go down here. This is going to be a minus 1 operation to go up. So let's just multiply down here. If I combine 2 and 3, I get 6. Then I go back to plus 1 land, and it corresponds with 5. So combining 1 and 2 up here gives 5. But in plus 1 land, it's just like, say, x plus 1 times y plus 1 minus 1 is the output. So x plus 1 times y plus 1 equals n plus 1. So if I'm in plus 1 land, all I'm doing is multiplying. So this weird seeming operation, if I go live in plus 1 land, is just an operation of multiplication, which is a lot simpler. So if I go to plus 1 land, my starting numbers 1, 2, 3, 4 are now 2, 3, 4, 5. I combine them. 2 times 3 is 6. I keep combining. I'm certainly going to eventually get 120, because 2 times 3 times 4 times 5, my original numbers, is going to make 120. And then I go back up to original land, and it's 119. So I just take all my numbers into plus 1 land, multiply them as much as I feel like, and get more numbers that also live in plus 1 land. And whenever I want to, at the end of the process or in the middle or whatever, I can go back to original land by subtracting 1 from all the numbers I currently have. So that's kind of the most sophisticated bit of this thing. But there's sort of one more thing to point out, which is, Tina, is that your name? Yeah. So Tina pointed out that when you did this thing with 3 variables, you get all three of them together, and then you get every possible pair, and then you get all the individuals. And that keeps going. Like one way to describe what you get with the numbers 1 through 100 is you get all 100 multiplied together, plus all the collections of 99 of them multiplied together, plus all the collections of 90. There's a lot of those, right? It's a gigantic thing. But it turns out this comes up really naturally when you're talking about polynomials and factoring and stuff. If you take stuff like, I guess we usually do minus so that the solutions are x equals a, x equals b, x equals c. For this problem, it might make more sense to do plus because these are all plus, but whatever. So when we work with polynomials, if we have a polynomial, we'd love to be able to write it like this, because then we can immediately see a, b, and c are the values that make it equal 0. And when you distribute this whole mess out, you get x cubed minus all of the things added up one at a time times x squared, plus, and the alternating signs are because the minus is there, all the things taken 2 at a time times x, plus, no, minus a times b times c, all the things taken 3 at a time. And so this thing somehow relates to like the polynomial whose solutions are all the numbers 1 through 100, right? And so actually, if we just go to this thing and we plug in like x equals, I guess we want these to all have the same sign so we can add them up. So if we make x equals -1, that'll fix them up so that this is minus, this is minus, this is minus, and then it's easier to add stuff up. So you can think of this as a problem about big polynomials and factoring also. But the real point is that what we want to do is we want to add 1 to everything. So now instead of 1 through 100, we have 2 through 101. We multiply them all together, so we get 101 factorial, and then we subtract 1, right? So the final output of this thing is this giant number, 101 factorial minus 1, which I don't even know what it equals. But one of the things I know is that factorials end with a whole bunch of zeros, so this thing's going to end with a whole bunch of 9s at the end of it, if I look at all of its digits. It's a pretty cool number. But what I really want to emphasize is that there's all these kinds of big strategies like symmetry and multiple representations and do an easier problem, and just keep coming back to these things because that's what really starts to make the difference in how you can solve problems.